We will now start with lesson 5 and we will talk about data patterns. This lesson introduces patterns related to data storage and access. After completing this lesson, we will be able to describe the sharding pattern and describe the materialized view pattern. So let's start with Redis Cache. So there are two primary cache mechanisms available in Azure, Azure Cache and Redis Cache. Azure Cache is deprecated and only exists to support existing cloud applications. All applications should now use the Redis Cache. So Azure Cache is a managed cache service that is based on App Fabric platform. You can create the cache instances by using third-party applications or Windows PowerShell commandlets. This cache mechanism is typically seen when working with custom cloud service roles. Redis Cache is an open source NoSQL storage mechanism that is implemented in the key value pair pattern common among other NoSQL stores. Redis Cache is unique because it allows complex data structures for its keys. Azure Redis Cache is a managed service based on Redis Cache that provides you secure nodes as a service. There are only two tiers for this service currently available. One is the basic tier, which is for single node. Other is the standard tier, which is two nodes in the master replica configuration. Replication support and service level agreement is included. So Azure Redis Cache provides a high degree of compatibility with existing tools and applications that already integrate with Redis Cache. You can use Redis Cache documentation that already exists on the open source community for Azure Redis Cache. Next, we move on to database partitioning. So most cloud applications and services store and retrieve data as part of their operation. The design of data stores that an application uses can have a significant bearing on the performance, throughput, and scalability of a system. One technique that is commonly applied in large-scale systems is to divide the data into separate partitions. Partitioning refers to the physical separation of data for scale. Modern data stores understand that data may be spread across many different instances, as the size of the sum data for the application can be larger than any individual physical store can handle in an efficient manner. Partitioning can improve performance, availability, and scalability, so any data access operation will only occur on a smaller subset volume of data, which in turn ensures that the app operation will be more efficient when compared to a query over the entire superset of data for your application. Individual databases can hit physical limits, which are also overcome when positioning or portioning data across many different individual databases. Partitioning also spreads your data across multiple nodes, which can individually be replicated or scaled. When a node is unavailable or being maintained, the application can use replica nodes. So what is the problem at hand? Hosting large volume of data in a traditional single instance store. So a data store hosted by a single server may be subject to various limitations. The first one is storage space. So a data store for a large scale cloud application may be expected to contain a huge volume of data that could increase significantly over time. A server typically provides only a finite amount of disk storage, but it may be possible to replace existing disks with larger ones or add further disks to a machine as data volumes grow. However, the system will eventually reach a hard limit whereby it is not possible to easily increase the storage capacity on a given server. Then the limitation is on computing resources. So a cloud application may be required to support a large number of concurrent users, each of which run queries that retrieve information from the data store. A single server hosting the data store may not be able to provide the necessary computing power to support this load, resulting in extended response times for users and frequent failures as application attempts to store and retrieve data time out. It may be possible to add memory or upgrade processors, but the system will reach a limit when it is not possible to increase the compute resources any further. Then you have the network bandwidth limit. So ultimately, the performance of a data store running on a single server is governed by the rate at which the server can receive requests and send replies. It is possible that the volume of network traffic might exceed the capacity of the network used to connect to the server, resulting in failed requests. Then you have the geography. So it may be necessary to store data generated by specific users in the same region as those users for legal, compliance, and performance reasons, or to reduce latency of data access. If the users are dispersed across different countries or regions, it may not be possible to store the entire data for the application in a single data store. So scaling vertically by adding more disk capacity, processing power, memory, and network connections may postpone the effects of some of these limitations, but it is likely to be only a temporary solution. So a commercial cloud application capable of supporting large numbers of users and high volumes of data must be able to scale almost indefinitely. So vertical scaling is not necessarily the best solution. What is the solution? Partitioning data horizontally across many nodes. So divide the data stored into horizontal partitions or shards. Each shard has the same schema but holds its own distinct subset of the data. A shard is a data store in its own right. It can contain the data for many entities of different type running on a server acting as a storage node. Sharding physically organizes the data. When an application stores and retrieves data, the sharding logic directs the application to the appropriate shard. This sharding logic may be implemented as part of the data access code in the application, or it could be implemented by the data storage if it transparently supports sharding. Abstracting the physical location of the data in the sharding logic provides a high level of control over which shards contain which data and enables data to migrate between shards without reworking the business logic of an application. And should the data in the shards need to be redistributed later? For example, if the shards become unbalanced. So the trade-off is the additional data access overhead required in determining the location of each data item as it is retrieved. To ensure optimal performance and scalability, it is important to split the data in a way that is appropriate for the types of queries the application performs. So in many cases, it is unlikely that the sharding scheme will exactly match the requirements of every query. For example, in a multi-tenant system, an application may need to retrieve tenant data by using the tenant ID, but it may also need to look up this data based on some other attribute such as the tenant's name or location. To handle these situations, implement a sharding strategy with a shard key that supports the most commonly performed queries. So Microsoft Azure supports sharding for Azure SQL database either by manually creating shards or using the Elastic Scale automated functionality. This example assumes that you are using the Elastic Scale feature. So scenario can be your music catalog application uses Elastic Scale to spread the large amount of data across many partitions. Each partition is an instance of Azure SQL database. The artist's unique ID number is used as the shard key. Alright, so next we will go ahead and talk about materialized view pattern, which basically generate pre-populated views over the data in one or more data stores when the data isn't ideally formatted for required query operations. This can help support efficient querying and data extraction and improve application performance. So when storing data, the priority for developers and data administrators is often focused on how the data is stored as opposed to how it's read. The chosen storage format is usually closely related to the format of the data requirements for managing data size and data integrity, and the kind of store in use. For example, when using NoSQL document store, the data is often represented as a series of aggregates, each containing all of the information for that entity. However, this can have negative effect on queries. When a query only needs a subset of the data from some entities, such as a summary of orders for several customers without all of the order details, it must extract all of the data for the relevant entities in order to obtain the required information. So what is the solution? So to support efficient querying, a common solution is to generate in advance a view that materializes the data in a format suited for to the required result set. The materialized view pattern describes generating pre-populated view of data in environments where the source data isn't in a suitable format for querying, where generating a suitable query is difficult, or where query performance is poor due to the nature of the data or the data store. So these materialized views, which only contain data required by a query, allow applications to quickly obtain the information they need. In addition to joining tables or combining data entities, materialized views can include the current values of calculated columns or data items, the result of combining values or executing transformations on the data items, and values specified as part of the query. A materialized view can even be optimized for just a single query. A key point is that a materialized view and the data it contains is completely disposable because it can be entirely rebuilt from the source data stores. A materialized view is never updated directly by an application, and so it is specialized cache. When the source data for the view changes, the view must be updated to include the new information. You can schedule this to happen automatically or when the system detects a change to the original data. In some cases, it might be necessary to regenerate the view manually, and the figure in the slide shows an example of how materialized view pattern might be used. Now the discussion question that you guys need to ponder on is, for the new application and database design, how would you select a partition key? Moving on, let's discuss some of the questions. So why would you want a periodic check or heartbeat of your Azure website's availability across geographic regions? So the answer for this can be, without a periodic diagnostic health check, you might not know for sure if your application is fully functional or not. So a health check can quickly inform you if your Azure platform service instance is running or not. Even if the Azure platform service instance is running, a health check can inform you if there is a fatal exception in your running workloads. The next question is, how could you implement the valet key pattern by using Azure services? So the valet key pattern can be implemented using any Azure service that utilizes SAS tokens, shared access signatures. The academic example would be to create a SAS token for an Azure storage blob that grants least permissive access to the blob resource from a client application. So these are some of the review questions that you should understand and try to answer on your own. So with this, we come to an end to lesson 5 and module 1.